Everything that happens around us, every physical phenomenon in the universe, is governed by four fundamental forces. Apparently, a simple falling ball has nothing to do with the formation of a galaxy, just as the force of a magnet has nothing to do with the formation of life. Yet all these phenomena occur thanks to the existence of the four fundamental forces. These forces are gravitational force, electromagnetic force, strong nuclear force, and weak nuclear force. They are called fundamental precisely because they do not derive from anything else. But what is the origin of these forces? How do they work? The fundamental forces are also called fundamental interactions. And to understand them, we need to go back in time about 13.8 billion years to when the universe originated with the Big Bang. The Big Bang theory is the scientific theory that explains the early moments of the universe when all matter and energy were confined to a very small space. In this extreme condition, the only thing the universe could do was expand. However, the Big Bang theory has a limitation. It explains how the universe evolved in these early moments, but we don't know exactly what happened at the very beginning at time tkt seconds. From quantum mechanics, we can know what happened for a time after 10 to 43 seconds. This is an infinitesimal fraction of a second, i.e. 0.42 zeros and 1 seconds. For us, it's practically zero, but not for physics. This very brief instant of time, during which the universe already existed, is called the Planck time. This does not mean that nothing existed before this instant, but the Planck time constitutes a limit to our knowledge. When the universe was only 1043 seconds old, its temperature was extremely high, several billion degrees Celsius. Initially, the four fundamental forces were unified into a single force, but after an infinitesimal fraction of a second, as the universe expanded and cooled, gravity separated first from the other three forces. Subsequently, the universe suddenly accelerated its expansion. During this phase, called cosmic inflation, the strong nuclear force separated from the other forces. Finally, electromagnetism separated from the weak nuclear force. Now all four forces act differently. In just 1 second, the size of the universe had reached a few light years, and its expansion continued for billions and billions of years. Matter aggregated to form stars, then galaxies, and the universe took on its current configuration, shaped by the four fundamental forces. The first forces observed by humans were gravity and electromagnetism because their effects are visible in the macroscopic world, while nuclear forces were discovered later because they act in the microscopic world and are therefore more difficult to observe. Let's start with gravity. We observe this force when an object falls downwards. But this is the same type of force that the Earth exerts on the Moon or the Sun exerts on the Earth. Among the four forces, this is the weakest. But without the force of gravity, we would be flung into space due to the Earth's rotation. Our Sun, as well as all other stars, is the result of a perfect balance between nuclear force, which tends to make it expand, and gravitational force, which tends to make it collapse. Without gravity, the Sun would explode. All bodies with mass exert a gravitational force on others. This force increases with the increase of the masses of the bodies involved and decreases with the square of the distance that separates them. The force that body 1 exerts on body 2 is the same force that body 2 exerts on body 1. Despite gravity being the weakest among the four fundamental forces, it is the only one to dominate on a cosmic scale. Only when large masses are involved can the effects of gravity be seen. This is why planets dance around the sun or galaxies attract each other until they merge. The most comprehensive theory that describes gravity is Einstein's theory of general relativity, which defines gravity as an effect of the curvature of spacetime. Einstein improved the application field of gravity as it had been described by Newton more than 200 years before. However, Einstein's relativity does not contradict Newton's theory of universal gravitation, but extends its application field. Therefore, to express the gravitational force that the Earth exerts on an object, or the gravity that the Sun exerts on the Earth, we can perfectly use Newton's law of gravitation. We can say that Newton's description of gravity is a subset of Einstein's description of gravity. The electromagnetic force can manifest as light, which is an electromagnetic wave, as electricity, or as magnetism. Additionally, the electromagnetic force governs the interaction between chemical elements and how they can bond with each other. All biochemistry and organic molecules have formed thanks to the electromagnetic force. DNA exists because the electromagnetic force holds molecules together, so we can say that without this force, life would not exist. The electromagnetic force manifests as electrostatic force between stationary charged particles and as magnetic force that acts between moving charged particles. Between two particles with the same charge, a repulsive force acts, tending to push them apart, while between two particles with opposite charges, an attractive force acts, bringing them together. Think that the electromagnetic force is 1036 times greater than the gravitational force and has the same range of action. But if electromagnetism is much stronger than gravity, why do we see the effects of gravity on a large scale and not electromagnetism? Larger objects, made up of billions of charged particles, should influence the behavior of smaller objects, yet this is not the case. Let's see why. If we observe the atomic structure of any element, we notice that the atom is composed of electrons and the nucleus is made up of protons and neutrons. Electrons have a negative charge, protons a positive charge, and neutrons are neutral. In an atom, the number of protons is equal to the number of electrons, and since they have charges of the same value but opposite sign, they cancel each other out, making the atom electrically neutral. This means that objects are also electrically neutral, and therefore cannot influence each other electromagnetically. If objects were not electrically neutral, then on a large scale the universe would be governed by electromagnetism. If we compare the force exerted between two charges with the force of gravity, we notice that the two formulas are practically identical. In electrostatic force, instead of having the product of the masses, we have the product of the charges, and it also decreases with the square of the distance. Both gravitational force and electrostatic force exert their influence at infinite distances. Despite the distance growing with the square, the force will become smaller and smaller, but never zero. Gravitational force, however, can only exert attraction between masses, while electromagnetic force can be attractive or repulsive, depending on the sign of the charges involved. Could this mean that there is also a sort of repulsive gravity that physicists have not yet discovered? This could be the topic for a new video. The strong nuclear force is the strongest force in the universe and acts on two different scales. We have seen that atomic nuclei contain protons, which are positively charged particles. But if these particles having the same charge tend to repel each other, what keeps them together? Here comes the strong nuclear force, 100 times stronger than electromagnetism, capable of counteracting the electromagnetic repulsion between protons, keeping them together. The strong nuclear force acts on an even smaller scale. Protons and neutrons are made up of smaller particles called quarks, the smallest elements of which matter is made. Unlike gravitational force and electromagnetic force, the strong nuclear force, instead of decreasing with distance, increases. Therefore, when quarks move away from each other, they are attracted by a greater force as if there were a rubber band holding them together. When quarks are very close to each other, the strong force has a repulsive effect, while when quarks move apart, it has an attractive effect. Its range of action is equal to the diameter of a proton, about 10 to 15 meters. The effects of the strong nuclear force are manifested in the energy released by atomic bombs through nuclear fission, in which the splitting of an atom into lighter atoms releases large amounts of energy. The weak nuclear force deviates the most from the concept of force, as it does not contribute to binding particles together, but to transforming them into other particles. It is the cause of beta decay, a form of radioactivity. The weak force is the reason carbon-14 dating exists, allowing archaeologists to determine the age of many objects by measuring the fraction of carbon-14 remaining in the object. In the nucleus of a radioactive atom, a neutron is converted into a proton, an electron, and an antineutrino. The transformation of the neutron leads to the formation of a new atomic nucleus, and therefore a new element. Nuclear reactors use beta decay to produce energy. The weak nuclear force has a shorter range of action than the strong nuclear force, about 10 to 18 meters. The four fundamental forces act through the exchange of mediator particles. For electromagnetism, when there are two electric charges, they interact through the exchange of a particle called a photon. Yes, exactly, the photon. The particle that moves at the speed of light is responsible for the attraction or repulsion between two particles, while the strong nuclear force acts through gluons, which are elementary particles that allow quarks to stay together. In the weak nuclear force, there is an exchange of mediator bosons Z and W. As for gravity, two bodies should interact by exchanging a particle called a graviton, but it has never been detected. Gravitational waves described by general relativity could carry gravitons. For years, physicists have tried to demonstrate that the four fundamental forces are simply different manifestations of a single fundamental force. The most successful attempt at such unification is the electroweak theory proposed in the late 1960s. At high energy levels, this theory unifies electromagnetism and the weak nuclear force. In the early 1900s, there was a physicist named Theodore Kaluza who tried to unite gravity with electromagnetism. In the late 1970s, the theory of grand unification emerged, stating that at even higher energies, the strong nuclear force and the electroweak force become indistinguishable from each other. This unification energy is so high that not even the most powerful accelerator built can reach it. Therefore, gravity is the only force that still cannot be unified with the other three forces. Researchers are trying to develop a theory of everything, capable of uniting all four fundamental forces of the universe. This unification is possible only at extremely high energies, equal to the Planck energy, as occurred in the early moments of the universe's expansion with the Big Bang. The Earth formed about 4.5 billion years ago, so its gravity, traveling at the speed of light, has covered 4.5 billion light-years. This means that an object located 4.5 billion light-years away is experiencing the gravitational effect of the Earth today. Sure, it will be a very small effect, but it's there. Thank you for making it this far. Leave a like if you enjoyed the video and subscribe to the channel.